When looking at bonding, the concept of electronegativity often comes up. Electronegativity is the measure of an atom's ability to attract electrons. Now, nonmetals have very high electronegativity. If we look at our nonmetals over here, they have very high numbers. We can see 2 point somethings, 3 point somethings, even 4 for fluorine. And then when we have on the left side, my metals have low electronegativity. I'm going to go over here. These are my metals. Have low electronegativity, and we're actually including my hydrogen over here because it's pretty high. Now, if we want to attract electrons, this kind of makes sense. If you figure, let's think back to a common compound, NaCl, salt. So if I have Na and Cl, we know that Na over here has 1 valence electron. And we know that chlorine over here has, if I were to count, 1, 2, from the left to the right, 3, 4, 5, 6, 7. So we're going to do 1, 2, 3, 4, 5, 6, 7. We know that chlorine really badly wants 8, and it really wants 1 more. It has a very high pull for electrons, so much more than sodium. Sodium wants to give away this one bad boy. He's like, if we look at sodium, if it gives up 1 electron, then it has a noble gas configuration. So sodium has a much lower, low pull for an electron. So it has a low electronegativity. It has a 0.9. I'm going to erase, there we go, I've made a mess there. 0.9 is its value compared to chlorine at 3.0. So chlorine is going to pull that electron. It is more electronegative. It wants to attract electrons, which is why nonmetals that have high electronegativity become anions. And it's also why over here, my metals with low electronegativity become cations, because they give them away more freely to become, my sodium is going to become a +1 charge, and my chlorine is going to become a -1 charge. All right, so this comes in handy because we're going to use these numbers to look at the species within a compound, and we're going to find delta E, which is the difference in electronegativity, and it actually indicates the type of bond. We just talked about ionic bonds and covalent bonds. Well, an ionic bond we know is when we have a metal and a nonmetal, and the metal gives away electrons to become a positive, and the nonmetal gains electrons to become our negative ion, and then they become this ionic bond. Well, we also know that an ionic bond has a difference in electronegativity of anything greater than 1.6. So let's look, for example, at Na and Cl. Na we said was 0.9, and chlorine was 3.0. So if I were to do 0.9 minus 3.0, I get a negative 2.1. I don't know why it says 2.6, 2.1. And then we take the absolute value of it. So 2.1. We would say that that's the delta E. And so because it is greater than 0.6, yes, it is an ionic bond. We can tell that difference in electronegativity. Now, these numbers you do not need to memorize. You will be able to use this chart on any quiz or test that you take. So don't feel overwhelmed by these numbers. We'd be able to look them up. So ionic bonds, anything greater than this 1.6. So let's look at another example here. Then we have covalent bonds. So notice here, there are 2 different types of covalent bonds. We have polar covalent and we have non-polar covalent. And what this means is, and we can see over here, let's look at these diagrams. See that H and Cl is, it's fatter over on this side of this diagram. Chlorine, if I look at chlorine up here, it has an electronegativity value of 3.0 and hydrogen is 2.1. So if I take the difference between 2.1 and 3.0, I get 0.9, taking the absolute value, 0.9. And if I get any numbers between 0.41 and 1.6, that tells me that it is polar. And polar is telling me that we have an unequal sharing of electrons, right? Because we know covalent is sharing electrons. Ionic is give and take. Covalent is sharing, but, and I'm going to write sharing down here too. They're both sharing, but polar means unequal sharing. Non-polar means equal. And we can see that by these pictures. We can see that right here, that there is an unequal sharing. Chlorine is much more electronegative. It has a greater pull, a greater attraction for those electrons, that it is pulling more. And if I look at two hydrogens, so up here, my 2.1, if I looked at 2.1 with another hydrogen of 2.1, so 2.1 minus 2.1 is 0. Anything between 0 and 0.4 is nonpolar, means equal sharing. And we can see that right here. See how that is a perfect oval because they are sharing those electrons equally. All right, so we can do another example here. If I looked at oxygen with carbon, so I'm going to look at oxygen is 3.5 and carbon is 2.5. So I would get a difference of 1.0. And we can see again right here, it's in between that 0.41 and 1.6. So this would also be a polar covalent compound, hydrogen and oxygen together, like CO2. And down here, if I looked at C and H, C is 2.5 and H is 2.1. So I have a difference of 0.4. And 0.4 tells me that it is nonpolar, so there is equal sharings of electrons. Now, we can also look at how to represent polar bonds. So polar covalent bonds are often labeled as dipoles in structures. It shows the unequal sharings, and because we were able to see the unequal sharing right here in this picture, but we're not going to draw pictures for everything. We just are going to be able to label it. And how we do that is the atom that has the higher electronegativity, which has more pull on the electrons, shows this, we draw an arrow towards it. So in that picture before, we saw that my H was over here and the Cl was over here, and it was like this, right? I mean, unequal sharing. Chlorine, so we would show it by drawing an arrow towards the more negative, the larger number, and then we put a plus on the tail end on the side that is less negative. And then we also show the side that is more electronegative. We show by doing this partially negative, or it's kind of like an S. So I always think of it as slightly negative. So it's more negative, it's the greater number. And then this side is the slightly positive. It's the smaller electronegativity number. And if you were also to go back to look at this electronegativity, we go back to our NaCl example. Na is the smaller number and Cl is the greater number. So, and the Na is the one that becomes positive, right? So we would not do this because it's an ionic compound, but think of when we're doing a polar compound, the arrow is going towards the bigger number, and Na became positive, so the plus goes on the side that is less, the lesser number. So we already did, so here's HCl. Now let's look at O and C. So again, if we go back and look at oxygen and carbon, oxygen was 3.5 and carbon is 2.5. Oxygen is 3.5, carbon is 2.5. And if we subtract those two, we get a delta E of 1.0. And we know that, again, coming back here, anything between 0.41 and 1.6 is polar covalent. So if it's polar, we have to show poles. And to show poles, we would draw an arrow towards the bigger number. The bigger number is 3.5. So we would do this, put a plus on that end of the tail, and the arrow is my slightly negative, and the plus side of the tail is my slightly positive end. Okay, so now we're going to look at a bunch of pairs here. We're going to figure out what kind of bonds each of these would form. And here's electronegativity numbers down here at the bottom. So if it is polar covalent, then we need to draw it in. I like to start by going, okay, well, do I have any metals? Because if I have metals, I probably have an ionic compound. So I'm going to go, oh, sodium, magnesium, aluminum, aluminum. Those are all metals. Let's see what they are bonded with. Sodium and oxygen. Oh, yep, that's ionic. Oh, that did not work. All right, magnesium. Chlorine is a nonmetal. Good. Nitrogen is a nonmetal. Ooh, germanium is a metalloid or a semi-metal. So that does not form an ionic compound. But I am going to write ionic and ionic. And we can prove that these are ionic. Because let's look at Na and O. So 3.5 minus 0.9 is 2.6, right? And having electronegativity of anything greater than, let's go back to our first slide here, anything greater than 1.6 is ionic. So for greater than 1.6, we are ionic here. Let's look at magnesium and chlorine. Magnesium is 1.2. Chlorine is 3.0. So that would be 3 to 1.8, difference of 1.8, which we know is ionic because it's greater than 1.6. Aluminum and nitrogen, 1.5 and 3.0. 3.0 minus 1.5 is 1.5. And again, ooh, 1.6. And that's okay looking at that other one. The qualifications, yes, it says 1.6. And this is really close, having our electronegativity at 1.5. But because it's so close, and because we have a metal and a non-metal and a large electronegativity difference, this one is going to break the rules just a bit and be, it is ionic. So now let's go and look at aluminum and Ge. So I've got 1.5. And where's my Ge? 1.8. So 1.5 minus 1.8 gives me 0.3. And if I go back and look, 0.3 is in this range of non-polar covalent. So we're going to write non. And that's okay, that aluminum's a metal. We know that, I mean, because Ge is not a non-metal, it's not going to be an ionic. And the difference in electronegativity is so low that is a nonpolar covalent compound. So then we need to look at, well, we already looked at H and Cl from before. We know that chlorine is 3.0, hydrogen is 2.1, and so we know that difference is 0.9, which is telling me that it's polar. So I'm going to have an arrow towards the larger number, a plus on this end. This is going to be my slightly negative, and this is going to be my slightly positive end. All right, so this is polar covalent. All right, let's look at nitrogen and oxygen. Nitrogen is 3, oxygen is 3.5. So the difference between 3.5 and 3.0, 0.5. So we know that this is polar covalent. So if I draw N and O, which one is larger? We know if I look at N and O, my O is 3.5, N is 3, so O is the larger one. My arrow is going to be to the right, a little plus. This is my slightly negative end. This is my slightly positive end. Let's look at silicon and phosphorus. Si is 1.8 and P is 2.1. So the difference between these two is 0.3, which is non-polar covalent. NP for non-polar. Sorry, it's a little messy. This pen does not write very well on my computer. And then let's look at silicon and oxygen. Silicon is 1.8 and oxygen is 3.5. So let's see, it's going to be difference of 1.7. My O is my greater number, so it's going to be arrow to the right, slightly negative, slightly positive. All right, so hopefully this helps you to see that we can use our electronegativity chart to look at the differences in electronegativities. My nonmetals have a greater pull. My metals have less of a pull. And we need to determine first if a species is ionic. Look at metal and a nonmetal. We then, if it's covalent, we determine the delta E to label if it's nonpolar versus polar. And if it's polar covalent, then we will draw the dipoles. Again, the dipole is the arrow is towards the more electronegative species, and the plus end of the tail is to the less negative species, which we say the more positive side.